It's my honor to introduce tonight's speaker. We have Dr. Mohammed Al-Faruque. He's the ConnectSync Broadcom Endowed Chair Professor at UC Irvine, where he leads the Center for Resilient Autonomous Systems and the Cyber Physical Systems Lab. He's a recognized leader in embedded and cyber physical systems with over 175 published papers, 12 US patents, and a Thomas Alva Edison Patent Award. His work has earned multiple IEEE Early Career Honors and UC Irvine's Mid-Career Faculty Research Award. He plays key roles in major ACM, IEEE conferences, and serves as an associate editor for several top journals. Dr. Al-Faruque earned his PhD in computer science from the Karlsruhe Institute of Technology in Germany. So please, let's welcome Dr. Al-Faruque.
Okay, thank you very much. Thank you for a nice introduction, and I hope you can hear me from the back. Okay, so I'll speak about cyber physical systems. A lot of buzzwords are here: cyber physical vulnerabilities, autonomous systems, and where we are today. And what I believe, some of these things that my personal belief and had been with this journey, and how I see the future. So I'll start with the examples, basically. So this is most of the examples is done in my lab. So I will mostly use the things that we are working in our lab. So this is the unmanned aerial vehicles, the drones name. And this is everywhere now, am I right? There are commercial products, people are using it for vlogging, for personal use, and law enforcement is using, and also there's other aspects, illegal stalking and harassment. So one of the applications of this system is basically what we call autonomous target tracking. If you see this example, and as I said, these are all physical AI. So AI is transforming to physical, it's becoming into the physical world. So that's why most of the AI that I will not speak a lot about AI in this talk, but anything that I speak AI, you will imagine that I'm talking about AI within a robots, in a drone, or this type of thing, just for a disclaimer. So this world of this tracking system, the question is how can we now interact and how can we fool this system? So one classic example that we have come, that adversarial attack model, that if we perturb the environment, what was the intended purpose of the system, can we basically make the system somehow in a way that the system is not able to do the intended purpose. For example, in this case, you will see this is an umbrella in this example that we, a printed umbrella here. And this printed umbrella is an adversarial attack because, we have tried to basically the optimization algorithm, if you reverse the optimization, Gaussian optimization, you will see you can create a adversarial patch or adversarial scenario where, you can eventually make the drone hijacked, or you can basically destroy that drone. So this is the scenario. So this is what we have been trying. So this is called basically, you want to attack the position attack, or you want to make sure that the drone cannot follow you. So we started working on this project 12 months ago. I will show how we were motivated starting in this project. So you see this video, small video, I don't know whether you can hear it, but this is the patch that, yes, so you see that the bounding box we are making just by umbrellas. We didn't change anything, we didn't touch the drone. We're basically using this umbrella, and the drone is basically coming close to you and changing the direction, and basically your intent and altitude is changed, and also the distance is changed. So this type of thing we have tested on different algorithms basically, and we have seen that you can, by perturbing the environment, you can do this type of attack in a drone. So these are different testing. I believe the videos are working, yes. So you will see that our students are working on both black box and white box drone, mostly DJI drone. The last one is a DJI drone. I think, yeah, but multiple commercial drones we have shown that, just by using this type of, umbrella or a cap or by helmet, you can basically make sure that the drone comes close or it goes far away. So this is just an example that now you see that the type of attack we are talking, just by perturbing the environment. So this is one type of attack that we can show that is going to happen. The second type of attack that I'll show, another example. So this is the airflow sensor. So most of the UAVs are equipped with airflow sensor because airflow sensor eventually help the drones or any of these unmanned aerial vehicles to precise control, and also help basically a lot of safety and resiliency in terms of turbulence and other things in wind and all these scenarios. And this is very useful, sensor to be used besides many other sensors. So what we started doing in 6 months ago, basically, we started looking into that how secure these sensors are, because I had been doing a lot of work on sensor security. And we started seeing that, if we shoot basically acoustics, if we can understand if this is the resonance frequency, those who are in the engineers, you will understand the signal processing. So this is the resonance frequency for this type of sensor. The second one is the resonance frequency for the other type of sensor. There are typically two different types of sensor in the commercial domain. One is basically temperature based, and another is basically in a static pressure. They use it static differential pressure sensor. Hardware basically another is differential pressure sensor. And in both you can find the resonance frequency. And within that resonance frequency, if you can shoot acoustics, either into ultrasonic region, but these are if you are into the audible region, you perturb the sensors, and you can basically, I will later show, you can basically put them out from the linear region. And by doing that, what you can take control over the drone just by acoustic or electromagnetic. So this is one example that my student is flying. This is a fixed twin drone, basically. The students love it. So this is one of the examples that we have tried to fly. And this is, you see that this is in the lab. This is in the simulation. I think this one is in the simulation. You'll see the results, what's happening. The point is that we can hijack the drone. We can destroy the drone using acoustics. And this is the type of thing, electromagnetic warfare that people speak about in DoD world. And we started working in this area, as I said, 12 months ago. And we have now a DARPA grant, big program going on. It's a $15 million grant that where we are looking into drones and UAVs or anything that is autonomous robots, that basically robotic vehicle or whatever you call it, from sensors all the way to actuators. So this opened up opportunities for us and our students to look at the full stack of current existing drones that apply mostly in the commercial domain. Unfortunately, UCI cannot work on things that requires clearance, because our students are coming from all different backgrounds. So we need to be working on mostly on the commercial part. But we have partner from DoD who are working, taking our technologies, whatever we are finding, they're trying to understand also into the classified portion. So there is a portion that is done into the classified part by different companies. So if you see the world going forward now, and if you see that for all these different, if you open up a drone that where we are today, you will see the lots of different sensors basically we are putting inside the drone. Ultrasonic sensor, microphone, GPS, IMUs, camera, LiDAR, radar, all different equipped with heavily, basically huge amount of thing. And there is a huge amount of this, physical AI world, all right? This physical AI world, we are putting algorithms either on board, or if the algorithm is extremely complex or basically require very high computational workload, we offload some of this computation. Or there is an entire talk I can give about that, or split computing, where is the right place to run this computation? Because this computation is heavily, am I right? At the end of the day, you are doing the perception, you are doing the planning, and then eventually you are doing the control of this drone. This whole 3 pipeline stages you want to do for this type of thing. So, and I'll try to motivate that every step here, you are opening up, you are bringing lots of functionality, lots of smartness, lots of actionable intelligence, I call it, not AI, artificial intelligence only, but a lot of actionable intelligence throughout this pipeline. But also you're opening up basically the possibilities of vulnerabilities in different scale. As I said, some of this example here, I try to get this thing from this paper that, all these sensors that we are today putting into the robotics vehicle, either it's autonomous car or a drone or robots that will be probably you'll be seeing in your workspace in future, I'm expecting, or in your home where you are using different IoT devices, you probably don't think that how many sensors are there. But as soon as you basically make things smart, you have to understand the very first thing for a system is to understand the environment. And just like a human understand the environment using our eyes, am I right? Our eyes, ears, our different perceptory systems. The machines also need to understand the environment using this sensor. And if the sensors are vulnerable, the very first entry point, that anything can be vulnerable. Am I right? Just, the dolphin attack, one of the examples that I like, it was in Alexa, basically, that you can play the audio into the ultrasonic range, which you don't hear, but your Alexa is hearing. And if you connect your Alexa with your door or with anything, that means someone can basically pass command into that region and do whatever he wants to do. So this is just an example, very useful example in a way. A few years ago, this dolphin attack came. So it's opening up an entire world of attack space, and both in commercial domain, our daily life, and of course the DoD life. So for our safety and security, these are definitely important aspects. So I think with these examples, there are many examples. I just wanted to show a few examples that I've done many examples in the last 10 plus years in my lab, but just pick recent 2 examples that my students are working on now, and I'm excited about. This project will continue another 1.5 years, so I'm sure there will be a lot more exciting things to talk to about. But why it's happening, am I right? The question is why part. As an academic, I'm always interested that where it's coming, and how do we basically eventually look into these systems and how it will influence our system building, our understanding, and eventually different research directions, and of course product development eventually. So if we go back to textual description, am I right? What is happening? So a couple of definitions I just want to bring to the audience before I go a little bit further. So this is firstly a very common term, that embedded systems. Am I right? Core of all this autonomous system is embedded systems, and I'm happy to take this definition from Peter Marvedel, and which I know all these people I know. That's why I took their definition, and I'm happy to talk. So Peter, in his book, first defined that embedded systems are information processing systems embedded into a larger product. Am I right? He's from Dartmouth, so he retired a few years ago. So that means we have seen, am I right? Very small computers, either you call it microcontrollers, or later for image video processing, it became phone, and all the big range of things that became embedded systems, and it transformed the world what we are today. IoT, then CPS, all these things. But the core part was embedded systems. And then, of course, Edward Lee from Berkeley started talking about that, what does it mean by embedded software? We know software, we are doing computer software, but what does it mean? What is the specificity of embedded software? So he said that embedded software is software integrated with physical processes. This is a good deal, that it has to be part of the physical process. That means it needs to deal with physical dynamics. That means differential equations. That means going back, that your state machine is basically working with the physical dynamics. And the problem then he tried to articulate that what is the technical problem? What is really the big problem within this? The technical problem is the managing the time. Now you see, and concurrency in computational system. So these are the 2 most important challenges that for the last several decades, who started with embedded system, myself we had been dealing with time, managing time. How to deal with time? Because every computing devices work in a different time, and how to synchronize this time. What do you mean by time? Because most of these embedded systems are deployed into safety critical system, and time is the foundation of this thing that you have to manage. And then concurrency. In a general purpose computer, when you manage processes, threads, PID, all this, there's a different world, different dynamics. But the question is, when you go into microcontroller and also distributed computing with Ethernet and all these things, what do you mean by concurrency, and how do you manage those concurrency basically? So these are a big deal. These are the big challenges, and I believe there has been tons of work, got matured, industry is happy, a lot of work got into real practice there. Then, the 2006 around, the US government in NSF, National Science Foundation, said that, okay, now let's take a newer challenge. I was still a grad student at that time. The challenge was that, okay, we have learned from embedded systems that in embedded systems, we need to understand hardware software design, like one of the things are hardware software co-design, understanding time, concurrency. It boils down to SoC design. Many things evolved eventually. But now if we want to take even the dynamics part into systems, like the physical world, either it's in chemical world or it's a biological world, or it's it's an electromagnetic mechanical world, and then put software in that. And if we want to optimize at that abstraction level, at the end of the day, as an engineer, we want to optimize things. If you want to optimize at that thing, how does it look like? And that's when it started. All these things started of cyber physical system. It was a new buzzword. And then eventually it became popular. Of course, first within the academic world, now I see with industry and many other places, government is speaking the language. But the technical problems that from the very early days, we started talking about that, how to manage the dynamics, because one is operating into the continuous world, the differential equations, and another is operating into the discrete dynamics. And then how do we basically put them together? What is the right modeling? What is the right abstraction to manage these dynamics? And of course, time is still a relevant problem, and it will stay a relevant problem. And concurrency into network computational problem. Before it was more like a single systems concurrency problem, but now we are more interested basically into understanding the network system. So eventually, the CPS started getting its root into this embedded system with a physical understanding, and we call it embedded systems plus physical environment. So I think this definition I wanted to give, to make the point that how things are moving and where I will go in autonomy and autonomous system. So you'll see the connection. So now if you want to take even a more intellectual understanding, I already mentioned that, the world of engineers are all about, mostly, except computer scientists, computer engineers, the world of engineers are full of differential equations. They optimize into this physical world. Talk to your mechanical engineer friend, or those I know, some of our colleagues or friends here came from aerospace company. I was talking, you deal with optimization into this differential equations level, and this is the Newton's world. I say Newton's world. And the fundamental thing is energy flow, and you try to optimize the energy flow as an engineer, different format of energy, doesn't matter, but you do that. And then, of course, interestingly, both of them are from Cambridge, am I right? Both of them are at the same place, just many hundred years apart. And this guy, and the story of Alan Turing is very fascinating to me. And this guy wanted to build a machine that thinks like a human. Amazing quest, amazing question to ask. And then when this guy wanted to do, I don't know, I'd never read anywhere, but I'm sure that he definitely had been trying to model a system that will think to break the Enigma machine. Many of you know the story, that he wanted to make a machine. And then, of course, this new type of mathematics that we end up with, discrete math or state machine, this type of abstraction, foundation of computation came, and that was very helpful. So, and all about here is information flow. I call it that, it's all about information flow, a lot of information flow here. We have used this type of mathematics in communications, networking, of course, computation, model of computation, and all these things. And at the end of the day, these are all about information, how information will go from one part to another state. And the question, and the way I see cyber physical system is that, now Alan Turing is trying to control the physical world. Am I right? That's what I always say, that, how this information flow and, through sensing, if we can create the observability and all these things. So this is the point that, I showed some example of security in autonomous system. I hope I try to explain what does it mean to be cyber physical in general. What is cyber physical systems look like? And then I will now go back to, again, security and why today's talk that, these cyber physical vulnerabilities are happening and why it's new. I'll try to articulate that why suddenly this buzzword came, cyber physical security, because why not cyber security here? That's the next question I'll try to answer. One of the examples, recent examples, I think it matters a lot. Am I right? Cyber warfare, we are always we know cyber warfare. What does it mean, cyber warfare? We have been talking about things for decades, that we know that how our network can get vulnerable. And we have been always concerned about that our infrastructure can get attacked. Am I right? If you think from United States point of view, we have lots of critical infrastructure. We want to protect it. We had been always saying that, these critical infrastructures are as good as, I don't know how the LAX airport is secure. We don't know how the 405 highway is secure, There are, because lots of sensors are there, lots of systems, computers are running for managing our traffic flow, our all this. And this is a classic example. I don't need to read and tell anything. We have seen the cyber physical attack really destroying the physical world. Things that have impact on physical system and life and death. That is, they definitely opened up a very new thought process for us that, this is the new world we're entering, and how basically we'll take it from there, and how we'll prepare our systems, and what we'll learn from this system. Right? That's a very interesting thing for me. And I envision that this is going to be, this type of examples is not one of. I'm sure there are many examples that we probably don't see much, but this was one of the things that we have at least learned. And if you go and read some of the speculation, you will see how software, communication, battery system, all these things are connected, and how you have to put things together. Now again, if you go back now again to textbook definition. So what again inside all this system, this is a very simple textbook control system example I took. So this is the physical world that you basically want to control things. And what you do, you try to basically use sensors, as many sensors. Same thing, I want to fly my drone. I basically have my physical environment. I want to understand my physical environment with sensors. That's why I'm putting cameras, I'm putting LiDAR, I'm putting radar, IMUs, and all other different sensors. And what it does, basically, I have the AD converter. Eventually, I want to transform this analog information to digital information. And then comes the computer. Honestly, then comes the computer, and the computer's job is to then do all fancy AI algorithm, whatever algorithm you want to run, decision making, and all these things. Eventually, once you have done, then you again try to convert this digital information to something, decision making, and control your controller. And that's why basically digital to analog converter come, and you use your actuator. In this case, we are flying, like the motors of my rotor, and all these drones needs to be drive. If it's talking about a battery system, your battery system can also be an actuator that you control the charge, discharge, and all this power getting out. And that's the classic example. So as I said, I was very interested to look into the whole system. So I started looking into the sensor part. I said, okay, if my drone is vulnerable and attack is going to through sensors, or if something is shooting, why should I basically investigate? Should I go to a cybersecurity guy? Because that's happening looks like, let's like analogy is that if I have problem, I have some problem that is related to my eyes, I don't go to basically my general physician. I go maybe, but I try to go to see my eye doctor. That what is my problem in the eye? That means I need to really look into the sensors. That what is the current state of the art design of sensors? That's what I basically started looking a few years ago. I started looking into how do we design today's sensor. So if you open up any sensor, most of the sensors, to be honest, most of the passive sensors these days, active sensors has a little bit different architecture, but most of the passive sensors, gyroscope, accelerometer, pressure sensor, like example I gave, you'll see that these sensors have this pipeline. You first basically have a sensing structure like a diaphragm. Most of the cases, if it's some sort of diaphragm, and then they produce basically very low usable signals, these passive signals, and then you try to use amplifier of this thing, and then use filters because it is very noisy data. It's a super noisy data, and then once you can filter using your different filtering technology, including the Kalman filters, and then definitely then you use the analog to digital converter, and then eventually it goes to a computer. So you see there are at least 5 steps or stages of sensors before even it goes to the computer. Then obvious question is that, is it possible to intervene as early as possible? Is it possible to intervene to say that before any malicious person inject a malicious signal, the red part I would say, into your sensor, is it possible to intervene and isolate and somehow differentiate this thing? And why we need to do that? Because if you see from a sensor's design perspective, this is the input signal in the x-axis and output voltage in the y-axis. You see that this is the linear region. Am I right? And this is typically the sensor's operating region. That if your input voltage signals, input voltage versus the output voltage, and that's the saturation region. So almost all sensors operate in this region. Now, only simple thing, these attacks are not doesn't need to be sophisticated, and that's also dangerous because even high school kid can orchestrate this type of attacks. So if I know what is my, like the example I shared, what's my resonance frequency, I can basically introduce that amount of power, voltage, and I can move the sensor into the saturation region. And the moment the sensors go into the saturation region, it becomes basically, it's useless because you take over the system. And that's the physics, that's the foundation basically. And rest of the talk I'll try to tell you that the question is that what sensors we have shown that you can push and how easy it is. I will try to show that how easy it is, to be honest. I don't want to show how difficult it is. The other way around, I will try to show how easy it is to push these sensors basically from their operating region to a saturation region. And now that is a tremendous problem for me. And of course, I spend a lot of time to design new sensors, but for the sake of time, I'm not going to give solution because the solutions are bulky. Solutions are not very sophisticated. Still now, like the sensors, one of the sensors that we have rebuilt is a Hall sensor, which is 190 years old type of thing. Is a state of the art in industry. Nobody is going to buy my solution or implement it. We have patented these ideas. But the thing is, nobody is ready to, because these are so cheap sensors that nobody is going to replace these sensors with, spend another couple of dollars to build this secure. But this is a step forward. I think how to build new secure sensor. What I'm trying to articulate, I will show and try to articulate that we need a lot of research to build new sensors that that can solve the problems into this 5-stage pipeline before it goes to the computer. So, as I said, these systems had been shown. A couple of examples I already told about the dolphin attack, but Tesla as autopilot was fooled by using a $300 projector, basically, and there has been the one that I just said that dolphin attack. Our lab has shown that $45 just by spending $45, I can hack into a solar inverter. That is basically most of your residential home has a solar inverter outside your home. Probably you never noticed it. So anybody can, even without opening up the solar inverter, I will demonstrate an example how we can do that. So all these things basically are eye-opening for me in general, that why these things needs to be discussed and even in fact integrated in our education system. As an educator, I'm very much involving these things into our education system. So this is the example that I was showing that I did around 2000 before COVID. I remember 17. This is a coffee mug that if you see close by, this is a coffee mug that all the electronics, Arduino board to create a magnetic field, electromagnetic field. It's nothing. It's an electromagnetic field, has a Wi-Fi capability and radio with a radio. I think my students spent $45 at that time. Now things are expensive a little bit. But $45, we were able to hide inside a coffee mug, and you can go anywhere in the world. You can basically log into your device and create the magnetic field. And using that magnetic field, the right amount of magnetic field, you can basically take over all the Hall sensors that is inside the inverter. And that was basically most of this inverter that you see today, grid-tied inverter. This is the inverter that we opened up. And you will see there are almost like 6 of these Hall sensors. 3 of them are used for current measurement, and 3 of them are used for voltage measurement in different stages of the control system. And though all these sensors are vulnerable, all the sensors can be vulnerable, and this you can eventually create these are the electronics. You can see this picture, and you can take over it, and you can hide it. You don't need to open up the solar inverter at all, and you can take over the grid. Even even if you want to do how you can take over the grid, because solar inverters, like this is a small one, but if you think about a solar farm where they are basically large inverter into 100 megawatt range, there are many farms in California, in fact, in that range, which I didn't have access. I cannot show you the results. We have shown it in simulation. But eventually, using such vulnerable waste, we see waste management and a thing left inside facility. That's why physical awareness is very important. What's left is in our, if it's a critical infrastructure, what's left and what's inside and what's going on, you can take over. So, this was the thing definitely got huge attention within the power grid community when we published this paper. It was definitely something, for me, it was very useful that, I was able to speak to a different domain people. By training, I'm a computer engineer, but, power systems is not my area, but telling their language and showing them that how things are will transform, it opens up the inter-conversation with a different group of people, and then definitely sophisticated solutions can come out of it. And that's what the reason that I'm showing that my work. Then we definitely try to take another example. Today most of the talk will be a lot of examples, to be honest. And this is another example, and this was basically during COVID. So during COVID, if you remember that clean room became very important, am I right? Especially in hospital. If you remember, ICUs became really serious things. We didn't have access, and and of course, different labs and all these things. So the common theme of negative pressure room, this is the negative pressure room in ICUs, pharmacy, research facility. If you go to a clean room from a semiconductor point of view, all these things have a clean room, am I right? And all the idea is that you create basically, this is the foundation, this is the architecture of a negative pressure room. That if you see the negative pressure room architecture, you will see that you have fresh air goes in and fresh air goes out, and in between basically you have this exhaust fan typically, and you have basically, if you are talking about a microbes, a biological facility, you keep your either deadly microbes inside that, or if it's a patient room, the patient is inside that. And all these things are controlled using this small hardware, and that's called the pressure sensor, and with some computers in that, am I right? So this pressure sensor looks like basically this is the differential pressure sensor. They have two ports. This is the diaphragm of the pressure sensor, this electric diaphragm, and this is very standard architecture. Every clean room you go, you will find this architecture, same thing. And the question that my students and I was asking, in the previous example, we had been hiding things in a coffee mug or a jar, am I right? The question that we had been asking, is there any other way, even we will not hide in a coffee mug? Is there any other even sophisticated way, without even going and leaving that thing? Can we basically try to make these sensors vulnerable? And I had a very good student, in fact, at that time. So he's now a professor in George Mason. So this is the clean room within UCI. Fortunately, we had clean room within UCI for semiconductor design, INRF. Those who are familiar with UCI, we can do chip design in the technology is old. We are trying to improve it. So these are some of these things. So what interesting thing is that you will see any clean room is equipped with CCTV, and there is basically a lot of microphone, and later I'll see that these are basically CCTV here, and we do it by design because we want to make sure that we can speak to the people in other rooms and all these things, communication, and this is a very common practice. So the question that my students are asking, that is it possible that we, rather than attacking the pressure sensor, can we attack those basically speaker system and eventually create a passive attack? And if we basically, for example, pass some of music, instrumented music with a certain, this is a hello from the other side of the world music. I think this is very spooky. And if you instrument with the same, because the pressure sensor are if you see the resonance frequency, this is in the audible range. So pressure sensor, I think we had 8 companies. We contacted 8 vendors we got all the pressure sensors that's more or less in the market. We tested, and I think majority of these pressure sensors are into the audible range. If it's in ultrasonic range, it's much easier, by the way. So when it's an audible range, the question is, in many cases, you can play music from the speaker, and through playing music, which looks naive that I'm playing music, and eventually you're passing your information. You're basically passing the same resonance frequency that will make this pressure sensor vulnerable. And that's exactly what we have done. And we have demonstrated that this is the log file from that room. And in fact, we had been trying to not tell them what we are doing, testing. And then these are the original log files, and these are the measurements that the facility was taking. And we played the music, and eventually we were able to create that attack. And of course, that was another good demonstration of that. You can attack many ways. And are these the 2 only ways? No, I'm sure there are many, many smart ways. And you'll see that in the last 5 to 6 years, there has been explosion of paper demonstrating that now different types of sensors that all are vulnerable. My group is working on cameras, lidars now to show that how these active sensors that you see, and because these are mostly used cameras are very much used basically these days, and they are vulnerable to many things. In fact, we are looking into electromagnetic impact and other scenarios. But today I'm not going to show those results. But these are also vulnerable. I am just telling. So you see that I hope that by this time I convinced that the things that were left behind before, that only cybersecurity or people are concerned, even your sensor is vulnerable. And there is an important we need to focus on that. We need to really build defenses. We need to really rethink that how do we build our sensors in a secure way. Of course, I cannot present it without showing that information processing, how vulnerable. But intentionally, I decided not to talk about anything cybersecurity. That because more or less we all are aware of it. But I want to give a different perspective. I want to say the premise of cybersecurity has been built with the notion that your hardware is secure. That means trust. The first decision was that we trust our hardware, and then we build our software. But the problem is that how to trust your hardware. And this is becoming a very prominent problem in supply chain because of, we don't build anything, a lot of things we don't produce in US. Our 70 to 80% chips are built outside the land. It's coming from offshore. And this whole supply chain of semiconductor design is absolutely, this is one of the research I do big time, but I'm for the sake of time, I'm not presenting. I cannot trust basically my hardware. And that's why I'm trying to articulate that these are also cyber physical attacks because hardware is physical. And once you basically cannot take the trust out of hardware, it opens up an entire different, dynamics. And we have seen how Intel ARM few years ago, if you remember, Spectra meltdown attack. They slow down their microprocessor because of speculative executions. It was all over the place in newspaper. This was a big thing. Stock price suddenly went down. So I'm sure you noticed it. I'm talking about a pre-COVID situation. So what I'm trying to say that this is also an area that is under discussed, and especially in research and education. I think this is something, I put some of this attack, that very common side channel attack, meltdown, Spectra, and hardware Trojan. The hardware Trojan is a supply chain attack. Am I right? Anybody can insert Trojan these days. And the Trojan can be as small as, I've seen a capacitor and 1 or 2 transistors. These Trojans can trigger, recently my student has developed a trigger, environmental trigger. That means just by calculating the temperature change in electric power, this power EV chargers, we can basically initiate the attack. That there are few transistors and few capacitor there, and they can act basically, they can be triggered and if you think from a vulnerability point of view and a scaling point of view, these systems are deployed in reality. So so my point is that this is another thing that we typically don't discuss and not aware of. But I'm happy that we are discussing even in the national level about supply chain. Many of these things are well discussed, especially component level, packaging level, even design when we are sending offshore design, what's happening, and definitely verification is even not done in land, some of these systems. Testing is done outside. So this is entirely open up the conversation that how we, going forward, we do build systems. The last example, I'll be talking again, probably not expected from you, that why an actuator is vulnerable. What is going on security aspects on an actuator? I should have presented this thing at the first because that's where I started my security research in 2014. Before that, I never wrote any paper. Even the paper that I will show was not submitted to a security conference because I never visited any security conference in 2015 until 16 that I was not aware of. I was interested in a very different story. That's a storyline that I was interested to understand the dynamics between the physical world, the definition I was talking about, and discrete math, and trying to see how, because of putting software in a hardware, this type of physical system, what is the leakage? What's basically leaking? And we bought a 3D printer, $300 3D printer from Best Buy, I believe I bought this thing. That I still have this very cheap, rudimentary 3D printer, and it creates sound. My interest was in 2004 that I wanted to capture the sound, and I wanted to show, and I printed this key, and then I basically used very simple signal processing, no machine learning even. Signal processing algorithm, I reversed engineered the sound. I reverse engineered the sound, and I was able to generate basically the G code line by line. And I was able to produce the key, see, not looking good, but almost close to dimension, only through sound. And then I used some post-processing, and with a simple example, almost 90%, I was able to demonstrate that just by sound, you can do that. So why it was so interesting? Honestly, when I did it, I did not also know that this impact will be so, it will open up so many things, conversation. And then, of course, later I did many modalities like power, vibration. So any mechanical system. In fact, when I spoke with my mechanical engineering friends later, I presented. In fact, this was presented also through NSF to the Congress. And then NSF initiated cyber manufacturing programs. And it is now, there is a conference about that. People basically took it to the next level. I know many people, a lot of vulnerabilities research happening. But this was the very first paper, I can tell you, that started talking about this acoustic side channel attack on an additive manufacturing system. The paper was published in a wrong place. But people picked up the work, and I'm happy that people picked up the work. And eventually, it became a major trend, and eventually, it was all over the place. In New York Times, LA Times, almost even many languages. I was interviewed by a radio in Austria, many places, because it opened up the conversation. And the next year, okay, before that, why it's happening? Let me just give you a little bit without going too much details. So these are the, when I say that in the physical world, what is the unique property of a Nefertiti, a thinking man, or Rolls Royce? Then the unique is that we cannot rebuild it. We cannot produce a second Nefertiti. We cannot reproduce. The moment we can produce, the company will be bankrupt. That's the problem. That intellectual, those people who create artifact, they want to retain their, retain their IP. I was recently in Marrakesh, Morocco. I was trying to take a video and photo of an artisan in the street. He was building something, and he entirely didn't allow me to take a photo. And initially, I was offended. Then I realized, oh, this guy is smart. If I record it, and he's probably concerned that, I may not be the right person. If I'm a wrong person, then it will be produced somewhere else, and he will lose his, intellectual property, and he will lose his artisanship. And the same thing here. It's a small scale, a big scale, because with the additive manufacturing world, we of course producing things in cheaper scale. But what we do, we writing the recipe into information technology. We're writing the recipe into software code, just like Python code. If you see the G code, it's very much like the Python code, and the Python code can be, as I showed that acoustic attack, you can reproduce the Python code, and eventually, if that is the type of attack you can do, then the privacy, definitely you violate the intellectual property privacy. And this may sound that, oh, this is so, why is useful? Interestingly, I was approached by a friend in biology department. The next year, once this paper got published, and he is into biology, he said that he synthesized DNA. He synthesized DNA, and I have no idea what DNA is, because last time I took my biology course was in high school, and all these things. And then, of course, this DNA machine I haven't seen. And then he was basically trying to do the same thing. He told me that the 3D printer and the DNA synthesis machine are exactly the same thing. Then I went and I said, okay, why it's important? He said, maybe your 3D printer, you're talking that, it's a toy example, but imagine about a DNA synthesis. They are really high-tech industry. And they are used into drug, medical, and crop optimization and all these things. It's a multi-billion-dollar company, and that's all sequence of ATCG. The question is, from this type of machine, now, this is just a simple example, and I know I'm probably taking more time, but yeah, this is the DNA synthesis machine, and you'll be surprised the sound. Yeah, they make sound like that, and it's so easy. It was very easy for me, by the way, to really recreate the synthesis. And when you produce, we were able to produce the exact sequence. We had been playing a cat and rat thing. The professor in biology department, he didn't tell me what he's printing, basically synthesizing. My students were just capturing the sound, coming back. And after a couple of iterations, we were able to demonstrate that we were, in fact, were able to steal it. And surprisingly, after a few months, I was approached by a journalist from, I remember, if I'm not wrong, it was from New York Times. And she told me a story that how some of this into agriculture domain, some of these IPs of these things were stolen not through this process, but this stealing of IP into this DNA world is a thing that's happening all over the world. US needs to protect their intellectual property onto this. She was talking about the agriculture, mostly crop and all these things that going into other country. So it was very fascinating to see. So I think I gave many examples today, without hopefully without too much of equations and other things. So I came up with this matrix a few years ago. So I was trying to articulate that, why this is different than cyber physical system, what I told in the beginning. So I created this 2x2 metric, what I call the impact layer and the attack layer, very simplified model. So for me, that cyber, if you attack into the cyberspace, if the impact is realized into cyberspace, that is the cyber security. And that's why your bank, your computer, you attack into the cyberspace, and attack is also realized. You don't destroy anything, you don't do this thing. But this is also changing, as I try to articulate, that because your hardware is not trusted anymore, if the moment you take out the hardware trust and you assume that hardware is a physical entity, it is becoming cyber physical. So this is really interesting to me to say. Your cars, where basically software is driving the cars or anything, I try to articulate that the impact is realized into the physical domain. That means that's why it's called cyber physical vulnerabilities. That's scary. Then through the 3D printer example, you saw that I try to show that with the physical domain, you also leak information and that also attack the cyber domain. The impact is realized into cyber domain, like the G code is stolen. That means it's a cross-layer attack. That means you cross the layer. And of course, the physical attack, that you attack from a sensor, which is in the physical domain, in the analog domain, and you try to basically go into cyberspace, change things, and then eventually it can reverse back, and the drones, you can destroy that drone. So eventually the attack is also realized into the physical world. So this is an entirely cross-layer cyber physical attack. Am I right? So, and it requires a new understanding, requires a new education process, research process, new tools, new methodology, basically to understand and validate and verify these systems. And I hope that this area will be discussed and will potentially basically develop many of these foundational stuffs going forward. So what is the takeaway from my talk today? What I want you to remember, if you don't remember all these examples, I want you to remember that this type of cross-layer security from these examples are real. And as I said, even in a small group with a professor and few grad students, if we can create this type of examples, then if there are large investment, large things behind, then there can be, things can be done in a different scale. Your hardware is not trusted. I think this is very important, and to start acting on that. Your physical environment is not trusted. I think this is something I am also emphasizing, that physical environment cannot be trusted, and that needs to be really thought in a different way. More scary part, that 2x2 matrix just talked about P2C or C2P attack, but attacks going to be created chain of attacks going to create, and that will be basically needs to be discussed. Those who are building SoC, those who are building systems using different layers, deployed into safety critical applications, part of human, used by human, cooperated by human, those systems. Human is an extremely, another interesting I didn't speak about, attack model, that human behavior, human in touch, those needs to be definitely bring into this understanding. Security is not a first-class citizen in design. If you talk to any CEO or many things, that's an afterthought. If something goes wrong, then come and patch it. So security, the question is that how do we want to bring it to the, because security is not a functional requirement. Security is a non-functional requirement. And our system design is functional requirement based. And how do we basically bring security and privacy into the design phase and building phase? And very important question is that, how do we train our student? How do we work together? Is it a simple computer scientist problem? Is it an electrical engineering problem? I want to say it's a multi-domain, and that's why we need to create multidisciplinary education system. We need to create a multidisciplinary conversation. We need to talk to people that maybe we haven't spoken before. Maybe we'll learn something from a domain that I'm not knowledgeable, and that definitely is interesting. That keep me very much interested to attend talks that I've never attended before and come out with something very interesting. And then, of course, defenses. If you want to think about defenses, that will consider basically cross-layer technique, because these defenses cannot be done by people in a particular domain. With that, I just want to thank my students. A lot of grad students who are currently working, a lot of grad students who graduated, went to industry. These are my 13 grad students. I think next year I'll be graduating 16, 3 more students. So it's a lot more students graduate. These are just PhD students. I think I had like 20 plus master student graduated from the lab. It's a lot of people's contribution, this examples creating. Just one thing that we have started, we are basically taking it to the next level. Our campus, University of California, Irvine, especially School of Engineering, started a new center called Center for Resilient Autonomous Systems starting July 1st this year. And we are looking into broader autonomy space rooted in AI integrated human cyber physical systems, where we want to look into this AI, machine learning, communication, computation, autonomy, control. And I know many of you are from industries around, will be very interested to collaborate with companies. As a director, I joined as a director of this center. And I'm putting things together at this point, but one of my missions will be that I really want to work with industries around, and then want to build an ecosystem where our students can really work with the companies. Definitely, federal government is our biggest supporter. I had been funded a lot by DoD. Most of my work has been sponsored by DoD, besides National Science Foundation and other agencies, and with that. And I want to thank them, all of them, for helping me in the last several years to do this exciting stuff. And with that, I will conclude my talk. Thank you very much. I'll be happy to take questions or your comments. Yeah, exactly.
Thank you, Professor. So my question is for the use case of the Tesla. What's the response from Tesla like? Did they solve the problem?
Yeah, they did solve it. This was the early stage, basically, problem that when Tesla was going through lots of changes. I don't think the current, I haven't heard anything from the current ones. Yeah.
Okay. And a follow-up question on the future architecture. Do you think AI is going to be playing a role like a lot of, I mean, in future, the way we can think of it is like inputs, which are sensors.
Yeah.
They're all feeding to LLM, and LLM is already trained for all these scenarios.
Yeah.
And then it can trigger it to an actuator. Like any thoughts on the future architecture of the systems?
Yeah, absolutely. You see that I was talking to someone from Google. Google Gemini has a robotics, Gemini robotics, and I think VLM, VLA, all of these things are basically going into that space and fusing text, voice, video, and trying to understand the context. And that's the future. You cannot deny it. That's going definitely happening. Yeah.
Sure. Thank you.
AI will be definitely playing a major role into this, and that will speed up the whole autonomy world in the next few years.
Yeah, the reason I'm asking is like because a lot of this they don't have a brain like in the architecture.
Yeah.
But that LLM could be that future brain where that it will also try to analyze the different scenarios coming from the sensors, and then it will make a decision that hey, this one we should do or we should allow or not allow.
Yeah, and it's not only sensor; it will come also from other.
Yeah.
That's interesting.
Audio, video. And
Yeah. Okay. Different modality, the way human thinks, basically similar.
Okay, thank you.
But that's also opening up a lot of vulnerabilities. Basically, the moment it's coming, the generative AIs. So many people are started investigating that. What will happen when the generative AI will be into this space, and what are the vulnerabilities here?
Hi, thanks for a great presentation. I will make a quick segue before I can ask the question. In industrial controls, these are the same problems that has been going on for past
40, 50 years.
Exactly.
Yes.
Actually, there is a book in UCI library that describes that. So the question to me is, what lessons, including even the standards that have been generated, have been incorporated in practices, anything from how the sensors are protected in industrial settings to deal with the issues of not necessarily even malicious attack, it's just accidental attack, all the way to the actuator, and then of course the enclosures. One of the issues is what enclosures do you use, like in this solar inverter that automatically may prevent some of the problems. It's a matter of money.
Yeah.
So what if any
wonderful question.
have you went to industry and said, you did it, give it to me,
Yeah.
and then I'll think about it?
Absolutely. Wonderful question. Fortunately, I'm aware of the industrial control system. I worked few years in Siemens before joining academia. So what is the fundamental thing that separation? Industry and control system has been separated from the internet. If you see, this was, yes, I'm coming. I was going to say that. So this was the last 40 years. When you said 40 years, it was the separation that industrial control system was never connected to, internet, TCP/IP, and going to the internet. And that was the first thing that we are not going to connect. Then definitely another thing was physical space security. Without trained operator, people are not able to access any asset. That's how in oil and gas industry, if you go any manufacturing plant, they had been trying to keep this thing and they were secure. Around 2006-7, with the name of Industry 4.0, mostly coming from Europe, they started saying, okay, we need to basically optimize our whole process by connecting things with, internet, so that CEO can even see what's happening into the process, into the back somewhere in Middle East, the gas industry, or the field in a remote area. That opened up definitely what you are talking about, the whole new PLCs are different now. PLCs are, I do a lot of PLC in my lab too. So PLCs are becoming soft PLCs with a standard protocol that in the commercial domain we are using. So I think this is still, the more they are opening, the thing was their opening was a little bit slow and controlled. The advantage the industrial control system had that they didn't jump into, because the business is controlled with few big giants, and they were able to go standardize it before they deploy it. Of course, there is a competition. I've seen with Siemens, GE, all these companies are basically coming up with it. And probably that's why you don't hear a lot of issues. But they, again, we have seen the PLC attack, if you remember, in Iranian nuclear power plant. That was the first time. I was at Siemens at that time, and all these things that you started seeing. And then obviously there was another attack around that time in Australia, basically wastewater plant. That was a Maruchi.
That was attack in the wireless.
Yeah, exactly. That's the attack in the wireless domain, basically, the Maruchi one. So these things are happening, and I think this is exactly the area covers this thing. So what I'm saying that, yes, this is thing. What you can learn, or what we probably should learn, but it's hard for learning in a commercial domain, is that in this domain, the things are not at that price level. Cost is definitely different, exactly. Money is a thing. Intention is a different thing. Competition is not standard, different level, and standards, nobody wants to follow the standard. They want to be the first in the market, want to bring the product as soon as possible. So that's why we cannot really sum up this thing, because there is no reputation here that company X can say that I control the product development. I think that's the problem, but that's problem, and probably we should do that. We should start talking about policy. We should start talking about more standardization.
And now that you mentioned the attack, for example,
yeah,
the original work in the area of the security was in the functional security. What happens if your programmable electronic system dies to your plant? Will it blow up? And there's whole work that was done in how to protect. Now, one of the ideas was to have
redundancy.
Basically, well, not so much redundancy. You have a separate system that provided the backup.
Okay.
And one example that it actually helped was in case of Saudi Arabia, where the operator went in to do the diagnostic on the system and found that the system was hacked from Russia.
Okay.
And it was description about 10 years or something like that, more than one of the trade publications. So here you had because of the way architecture was set up, you ended up detecting cyber attack based on your physical requirements. And this is the type of problems that industry has run across. Whether or not they found the solution, that's another issue, but something that could be brought in
Absolutely.
and say, let us look into that because we have time in academia,
Yes.
which industry does not.
Yeah, and also, not only that attack, what other functional, and it's an interesting thing. I did not know about that, but this is an interesting example. Yeah, I'll definitely like to know about it more. Yeah.
Hi, great talk. Very scary. I kind of come from the medical device world. I was wondering if you would consider things like automated defibrillators or insulin pumps to be
Absolutely,
cyber physical, and if you've
ARPA-H has a now big program going on biomedical devices, on security and vulnerability on biomedical devices.
okay.
All
Yeah.
these devices have the same problem. Unfortunately, I cannot work because most of these things are closed. Basically, most of these biomedical devices, and but as I said, there are sensors. There is a controller going on, and AI people are putting even ML algorithms there. This is something it absolutely will suffer from the same similar attacks that I was showing today. So
Okay. Thanks.
I'll be very interested to learn more, and yeah, absolutely, yeah,
Same types of issues. Yeah.
absolutely.
Thank you.
To answer, yeah.
Thanks for the talk. I think, yeah, it was good to cover kind of what you and your team are focusing on, and I'm glad to see that folks like you are pushing this information and knowledge onto the students who are going back out there into industry. And my buddy and I, we come from the cybersecurity industry, so we're well aware of the things that you're talking about. And frankly, there's lots of tools and capabilities out there. I mean, from NIST and CISA, a lot of government organizations that have put information about how to properly do product security for all these different critical industries. But there are a lot of technologies available to help with better understanding the systems that you're working with, both from a reverse engineering standpoint, from a cryptography standpoint, even from an application hardening standpoint, to prevent things from being viewed, as well as better understanding where the vulnerabilities or malicious software sit. So talking about supply chain, that's a huge issue. Making sure that your first and third party technologies are clean and don't have any back doors in them. I mean, you've got so many different examples, especially in the medical device field, like the contact backdoor. There's lots of different examples of the things that you're talking about, which bridge the digital software piece to the hardware, and then that could, of course, end up harming the public. But I'll definitely reach out and share some ideas.
Oh, that'd be wonderful.
From gaming security to application security in medical devices and control systems. There's lots of technology out there that has solved some of these issues, but I also feel like industry needs to push back that knowledge to academia as well to share.
Yeah.
So,
and I think
point.
that's the missing puzzle now. That the students that we are training, and the students are going out, they don't appreciate or understand the basically behind the scene what's happening and why, and also the courses and all this education system needs to be preparing them for handling this type of situations.
yeah, and we've got to learn from the past. Let's not forget all these.
Absolutely, as he said, we have to learn from other discipline and
Yeah.
from the past. Yeah.
Stuxnet is another great
Yes,
example.
Stuxnet was a big problem. Yeah.
And that was offensive. Just like Israel used the pagers to launch an offensive attack. The U.S. has done that as well, and it's all based on reverse engineering something first. Using things like Ghidra. But in that
I know
case,
Ghidra. I use Ghidra.
they pushed Ghidra back. Yeah. So that's something I want to talk to you about. We built something on top of Ghidra.
Oh, I was just working on a big DARPA project using Ghidra. We just basically launched some of this product based on Ghidra.
We're looking at behaviors of applications rather than just what's in them.
Oh, okay.
So
I was doing function name predictor. Basically, I was reverse engineering the binary code and basically going all the way to function name predictions.
yeah,
This
function.
was Exactly.
Yeah. Okay.
Oh, we should talk
Might be
about it.
interesting. Yeah.
Absolutely.
I'll share a link.
Absolutely. Yeah.
You mentioned the use of AI in the drones. Now, there is an Estonian company that is working on the problem for the war in Ukraine with Russian Federation of the jamming, and by using the AI to read the maps and compare it to the physical environment and deal with the issues such as changes because, for example, vegetation may have grown or alike. What efforts have been done in academia, whether it's UCI or somewhere else, to take that knowledge, or at least that approach, to deal with the issues that you mentioned, for example, the umbrella or something of that nature? And another item of it, a little bit of a reasoning it. We had a person out of sudden with umbrella. Does it make sense?
Oh yeah. Oh, human studies.
Basically,
Absolutely.
basically, the if I am saying that somebody
With
is
an umbrella, why this?
this doesn't make sense.
Absolutely. Absolutely.
It's basically in the military they are looking into projecting the basically
Laser and
force. Not so much the no, literally the holograms to
I know that they're doing it. Yeah.
to basically
Absolutely.
fall.
Camouflage the things and all.
Not just camouflage, but basically say, yes, we're here. Look at our
Creating a
tanks.
scenario.
Look at our planes, but there is nothing there except for the hologram. So again, those issues also come into play, and I'm curious what effort if any, is being done currently to look into that aspect.
No, they are doing. I'm aware of one of my collaborators who is basically looking even beyond this type of virtual creation of things and deletion, like the classic example, traffic light, putting some stickers and here and there. There are many people are working on that. Yeah, I'm aware of that. There is a significant effort on that going on. Yeah, all these things are interesting observation that you said, and these people are started exploring these things into this commercial space. The interesting thing is that a lot of things are known by DoD. A lot of things had been well known by DoD, but I was talking about that. But still, with the knowledge, basic academic world, a lot of things are coming as a knowledge for us, new things, and we are exploring and also disseminating to the students and trying to show that how they need to build the future defenses eventually. Yeah. Okay. So thank you very much. Yeah, Paul, listening. Thank you.